Our sun is a model of cosmic stability. It has been steadily fusing hydrogen into helium for 4.5 billion years, and it will keep burning quietly for 5 billion more. But scattered across the sky are stars of a completely different class. Take the bright blue supergiant marking Orion's foot. It contains over 8 times the mass of our sun. You might assume more fuel means a longer life, but the immense gravitational pressure inside these giants forces their fusion reactions to run at a drastically higher rate. They burn through their entire fuel supply in a fraction of the time. When that fuel inevitably runs out, the death of a massive star produces a sequence of events so extreme that the normal laws of physics begin to break down. The outer layers are obliterated, but the real mystery lies in the impossibly dense, dark object left behind in the core. In a fraction of a second, an explosion tearing outward at 10% the speed of light vaporizes everything in the surrounding solar system. To understand how matter can be crushed into the object that survives this cataclysm, we have to rewind. We need to track the violently accelerating countdown to this star's death. For millions of years, a massive star exists in a delicate tug-of-war. Gravity continuously pulls matter inward, trying to crush the star. In response, the immense heat generated by nuclear fusion pushes outward. As long as those two forces remain equal, the star survives. When the core runs out of hydrogen, it contracts, heats up, and begins fusing helium, then carbon, then neon. With every new element, the star requires higher temperatures to maintain that outward push, and the timeline shrinks catastrophically. Hydrogen burning lasts millions of years. Carbon burns for a few hundred. By the time the star is fusing oxygen, the fuel runs out in just several months. Then comes the final warning. The core begins fusing silicon, a stage that lasts for exactly 1 day, 24 hours. The product of that 24-hour sprint is iron, and iron is a thermodynamic dead end. Every previous stage of fusion released energy, pushing back against gravity, but fusing iron atoms together actually absorbs energy. It takes heat out of the system. The outward pressure simply turns off. After millions of years of perfectly balanced equilibrium, gravity is suddenly left totally unopposed. The star's fate is sealed. There is a precise mathematical threshold for what happens next, calculated in the 1930s by astrophysicist Subramanian Chandrasekhar. As the heavy iron core grows, it approaches a strict maximum weight of about 1.4 solar masses. Cross that Chandrasekhar limit, and the electrons inside the core can no longer support their own weight. Gravity wins completely. An iron core roughly the size of a small planet implodes down to a sphere 12 meters across, and it does this in less than a single second. The collapse generates terrifying momentum, with infalling matter reaching speeds near 70,000 kilometers per second, nearly a quarter of the speed of light. The friction and pressure of this implosion push temperatures over 100 billion degrees. In an instant, the intense energy rips the iron atoms completely apart, shattering billions of years of carefully constructed nuclei back into raw, individual protons and neutrons. Physicists call this photodisintegration. The gravitational crush is so severe that it forces electrons to physically merge with protons. This process, known as inverse beta decay, squeezes the opposing charges together to create pure neutrons, releasing a ghostly subatomic particle called a neutrino in the process. Trillions upon trillions of these neutrinos flood outwards simultaneously, carrying away 99% of the gravitational energy released by the collapsing core. Over the span of just 10 milliseconds, gravity has crushed the empty space out of matter itself. Atoms no longer exist. What remains is a free-falling, rapidly shrinking ball of pure quantum particles. But the collapse doesn't continue into infinity. It hits a physical wall created by a rule of quantum mechanics formulated by Wolfgang Pauli. The Pauli exclusion principle dictates that identical fermions, like neutrons, cannot occupy the exact same quantum state in the same location. The neutrons stubbornly refuse to be squeezed any closer together, creating an indestructible outward push called neutron degeneracy pressure. The core suddenly halts. The infalling outer layers of the star, still rushing inward at incredible speeds, crash into this unyielding quantum wall and violently ricochet back outward. As the shockwave races outward, it stalls against the heavy infalling material. But that massive, invisible flood of escaping neutrinos slams into the back of the shockwave, depositing just enough energy to revive it and blast the rest of the star outward in a supernova. We can see the echoes of this violence in space today. The explosion violently scatters heavy elements, the building blocks of planets and biology, out into the galaxy. But behind the expanding clouds of glowing debris, at the exact center of the blast, a dark, silent object remains. The remnant is a sphere roughly 20 kilometers across. It contains more mass than our entire sun, packed into a space smaller than the city limits of a mid-sized town. If you could extract a single cubic centimeter of this object, a piece the size of a sugar cube, and place it on Earth, it would weigh roughly 230 million metric tons. It would instantly punch through the Earth's crust and sink to the core. Because the vast empty spaces inside normal atoms have been entirely eliminated, this object acts as one continuous, impossibly dense nuclear fluid. And because it retained the angular momentum of the massive star it used to be, it spins dozens, sometimes hundreds of times every single second. This is a neutron star. Its magnetic field is trillions of times stronger than Earth's, radiating intense beams of electromagnetic energy from its poles as it relentlessly rotates. It exists right on the physical cliff edge of becoming a black hole. If it had accumulated just a little more mass during the collapse, gravity would have pushed past the quantum resistance, and the star would have vanished entirely. Instead, it is held up essentially forever by the quantum stubbornness of its neutrons. A neutron star is the universe's most extreme laboratory, an object where the crushing weight of gravity and the microscopic rules of quantum mechanics locked into a stalemate, a permanent spinning monument to the exact millisecond gravity finally met its match.